So today we're going to go over the remainder and factor theorems. The remainder theorem says that if we have a polynomial and a complex number, we can figure out what f of that complex number is by dividing them and taking the remainder. So take a function, divide by a linear polynomial, and the root of that polynomial, the remainder of that division will be the same thing as if you plugged in c into the function. So let's prove it. Let this be a polynomial and that be a complex number. So what we can do is we can say, all right, what is f of x? What happens when we divide a polynomial by a linear binomial? Well, we always get a quotient and a remainder. Sometimes the remainder is 0, but that remainder is going to be a number divided by x minus c. Hopefully you agree that every time we divide some polynomial by a linear binomial, we'll always get out a quotient and a remainder, and that remainder will be written in fraction form as r over x minus c. Now, what I'm going to do is I'm going to multiply both sides of this by x minus c, because I want to get rid of that x minus c. If we do this, those cancel, and we're left with f of x. When we distribute that x minus c, we get x minus c times q of x, and the remainder, the x minus c and this x minus c cancel out over here, so we're left with just the remainder. Now, what the claim was that f of c is a particular thing, that it's the remainder. Well, let's plug in c into this equation. We get f of c equals c minus itself times q of c plus r. So simplifying the right side, we get f of c is 0 times q of c, so this whole thing is 0 plus r, which means that it equals r, which was what we were trying to prove, that the remainder is equal to the result when you input c. So we've proven it. The factor theorem says that x minus c is a factor of f of x if and only if, that's what the if with the extra f means, if and only if f of c equals 0. I'm not going to go through the whole proof of this, but the basic idea to show this direction, if this is a factor of f of x, then we're just saying, okay, f of c equals c minus c times something else, because x minus c was here, and then we substituted in c there, so we get 0. So that's one direction of the proof. And the other direction of the proof is saying that, okay, if f of c equals 0, then that tells me that the remainder is 0 when we divide by x minus c. Therefore, this had to be a factor. Whenever the remainder is 0, that's what we call a factor. So that's the basic version of the proof. You can certainly look up a more detailed proof if you're interested. So how do we apply these things? So the remainder theorem, remember, says that when we divide by x minus the root, then that gives us the same thing. Then the remainder is the same thing as inputting the 2. So, of course, you could evaluate this by plugging 2 in here, but what this is claiming is that this is the same thing as the remainder of g of x over x minus 2. And the easiest way to do this, I think, is with the synthetic division. So rather than having to substitute 2 in, you can do synthetic division with the polynomial we were given. Note that I put in zeros for x squared and the x term. So the remainder, when we do the synthetic division, will be our answer. And you can check check it by plugging in 2. But 3 comes down here. 2 times 3 is 6. These add to 4. 2 times 4 is 8. 0 plus 8 is 8. 2 times 8 is 16. 0 plus 16 is 16. 2 times 16 is 32. And 11 plus 32 is 43. So what I am claiming is g of 2 equals 43 because of the remainder theorem. F of, what was that? F of 2 is the remainder of f of x divided by x minus 2. So I divided by x minus 2, I got a remainder of 43. That's what it says. If this is a factor of that polynomial, then what is the value of b? So in this particular case, instead of using the remainder theorem, I'm going to use the factor theorem. The factor theorem says that this is a factor if and only if f of 7 equals 0. So once we know this, then we know that f of 7 for this function equals 0. So we can say, okay, what's f of 7 here? We know f of 7 is 7 cubed minus 10 times 7 squared plus b times 7 plus 5. If we simplify that, 343 minus 490 plus 7b plus 5. These add to negative 147. I just chose random numbers here. So this is what f of 7 is, and we know that f of 7 equals 0 because we were told that x minus 7 is a factor. So we can set this equal to 0 and then solve 142 equals 7b, divide by 7 on both sides, so 142 sevenths is the value of b. And those are the remainder and factor theorems. Once again, you can use synthetic division by c to find the value of f of c. And the other thing is that once you know that a particular linear polynomial is a factor of a function, then you know that when you plug in that number, the function has to equal 0. Thanks.